Welcome and hello. This is a video exercise in MODSIM, and in this exercise, we're going to be dealing with groundwater pumping. We're going to be looking at pumping costs and pumping rate and see how that interacts with other elements in the model. All right, so let's go ahead and get started from the beginning. I'm going to sketch in a network starting with a non-storage node. I'm going to just drop that in right there. Let's call that NS1, then move that to the side and zoom in. Okay. Next, I'm going to add a consumptive demand node right here. I'll call that D1. Downstream of that, I will have my sink. Okay, let's go ahead and connect those elements now. Non-storage, the demand to the sink. Now let's add our pump. I'm going to add a consumptive demand node right here, but I'm going to call it P1. It's not going to actually have a demand, but what this node is going to do is it's going to serve as a pump. Just think of it as a groundwater pump location, just like NS1, which is going to have some inflow, so will the pump. All right, let me move this right up there. Okay. I'm going to go ahead and start defining some of the properties. So the inflow at this NS1 node, I'll go right click, open up the properties dialog box. And then in the flow rate, I'm going to paste in the column of data I have saved. It's going to start at providing 10,000 acre feet of water every month flowing downstream to demand D1. And then that's going to slowly decrease 1 month at a time. So if we look at the plot here and then click on bar for the radio button, we see that decrease of what is it, 500 acre feet per month each month. Okay, click apply and click OK. All right, so for demand node D1, let's go ahead and look at the general. I'm going to leave it at 100 for its priority number right now. And then for its demand, that's on the time series tab, I'm going to say it's a constant 8,000 acre feet per month. Apply and OK. All right, next for our pump station, which is this consumptive demand node, P1. Let's open that up, and now we have the general tab. I'll just leave the priority at 100. The groundwater tab is what we need to do. For the time series tab, I'm just going to leave this at 0. There's no actual demand at this node. It's just serving as a groundwater pump location to provide water for the network. So here's the groundwater tab. I'm going to say it has a pumping rate of 10,000 acre feet per month. It doesn't necessarily going to pump that much water. It just has that capacity if it needs to. For the pumping priority, I'm going to set this to 5,010. Such a large priority right here means it actually has a positive cost of 100. The user's manual here has that equation. This is under demands, but it's the same equation. Cost right here associated with a node is going to be negative 50,000 plus 10 times that priority number. So if the priority number right here is 5,010, then this term right here comes out to 50,100, and then subtracting 50,000 would just be a cost of 100. So that's what I mean by cost of 100 based on this priority pumping of 5,010. All right, let's go ahead and run the model. Click apply, click OK, see what we get. I'm going to save it first. Let's go ahead and think about what do we expect to happen here. Exercise 17. All right, what we expect to have happen is we have a demand of 8,000 acre feet, which will be satisfied by this non-storage node inflow for what was it, the first 4 or 5 months until that inflow decreases below 8,000 acre feet per month, at which time the groundwater is going to have to supply the remaining demand as it increases from 0 up to whatever, as long as that demand is met. So let's go ahead and run. Click OK. Okay, so that ran. Let's take a look at the flow through each of these links now. I'm going to toggle on the graphing mode here, do a single left click on all of the links, minimize that, single left click, and a single left click. Okay, let's bring up that plot. Here it is. Okay, I'm going to toggle off some of these values. Here's the first series. This is the flow from the non-storage node from 10,000 down to about 4,500 at the end of the year. That's pretty straightforward. The flow from the pump station P1 to our demand D1 is this time series here. It's in orange and it starts at 0 for the first 5 months or so. And then after that, it slowly ramps up. That way, the sum of the values for this inflow in dark blue and the pumping would be at least 8,000 acre feet per month to satisfy the demand at D1. Now, in the event that that sum is greater than 8,000, then we'd have some flow in this downstream link from D1 to the sink. And that's what this plot is right here. This line with the dark orange is basically just the difference between the sum of blue and light orange minus 8,000. All right. So the pumping is only taking place because it has to supplement the demand at D1. Next, what would happen if we set the pumping at P1 to be a maximum of not 10,000, but 2,000? According to this plot right here, we're able to increase the pumping from 0 up to 3,500, it looks like. But if the maximum pumping at P1 was capped at 2,000, then it would probably just keep a straight line right here. And then that would invoke some shortage at demand node D1. So I'm going to go right click on P1, open up the properties, click on the groundwater tab, change 10,000 to 2,000, apply, okay. Then let's run the model once again. Okay, so I still have my graphing mode on. Let's check out the results. This is the flow from NS1 to D1. No surprise there. So here's our flow from P1 to D1. And yep, as we expected, it sort of is capped at 2,000 acre feet per month. And what that means is we should have a shortage at our demand node. So let me go ahead and open that up. Here is the surface inflow. It starts at 8,000 acre feet per month for most of the year. However, towards the end of the year, it's not getting that 8,000 acre feet anymore. The demand is up here at 8,000, and then the shortage is slowly increasing towards the end of the year, simply because the sum of the inflow from NS1 and the max pumping capacity of 2,000 acre feet per month from P1 is not enough to satisfy that demand of 8,000 acre feet per month. So what would happen if we added a second pump identical to P1, but with a different priority? Let's go ahead and do that. So I'll add another consumptive demand node. I'll call it P2, and then I'll edit the properties, which are right here. Okay, so general, that's fine. Time series, that's fine. And then for the groundwater tab, I'll say this is, again, 2,000 acre feet per month. Pumping priority, I'll say this is a slightly higher pumping priority number. So pump one was 5010. This will be 5020. So 5020. Click apply, click OK, and then draw a link from P2 to demand node D1. And then let's go ahead and run that. All right. So that ran. We still have our graphing mode on. Cool. All right. So I'm going to click on NS1. There's that. And then the flow from pump P1 and then the flow from pump P2. Okay. Here is our plot. We can see the inflow again from 10,000 dropping down to 4,500. And then pump P1 is this light orange and it pumps up to 2,000 acre feet, which is its maximum. And then pump P2 is the dark orange. It pumps up to what looks like 1,500 acre feet per month. It hasn't quite reached its max, which leads me to believe that adding this second pump P2 is sufficient to satisfy the 8,000 acre foot demand per month at node D1. If we wanted to do one more iteration and sort of stress the system, I could increase the demand at D1, say 8,000 to 10,000. Click apply. Okay. Let's go ahead and see what the plots look like now. All right, so here is the first link. Let me minimize that and just click on all the links and then open that dialog back up. Okay, so here is that plot. The only difference is that the pumps turn on earlier in the year. So here's pump one. It maxes out at 2,000 acre foot per month at about May. And then pump two turns on at June, I believe, and then maxes out, 4 months later in September. And then after that, we would have some shortage at demand node D1. All right, so let's go ahead and switch gears. Instead of looking at the pumping priority, let's go ahead and look at pumping cost. To do that, I'm going to go ahead and reset some things in the model. I'm going to delete node P2. I'm going to change the demand at D1 back to where it started at 8,000 acre feet per month. The user's manual mentions that in MODSIM, groundwater pumping is assumed to provide only supplemental water supply to satisfy demands after other water supplies have been exhausted. And the way that's controlled is through the costs. So when we clicked on groundwater here for pump P1, we have this pumping priority that calculates to a pumping cost. If I bring my notes onto the screen here, we have a pumping priority of 5,010 that equates to a pumping cost of 100. And the sum of 100 to pump plus the satisfied demand of negative 49,000 is definitely negative, and that's why the pump will pump. But if we change the cost by changing the priority of that pump station P1 large enough such that it doesn't even make sense to satisfy the demand. The pump of costing exceeds the penalty involved of not meeting the demand at the downstream demand node D1. That's possible if our priority is high enough such that the sum of the pumping cost and the demand satisfaction cost is a positive value. So what I'm going to do is change the pumping priority to 90,901. That's going to equate to a pumping cost of 49,010, which added to negative 49,000 is 10. It's a positive number. And then I'm going to just confirm that boundary by tweaking the pumping priority down to just two less than it was previously, 98.99. That would result in a pumping cost of 48,990. And when added to negative 49,000, it would be negative 10, and the pump will run. All right, so that's what we're going to do now. If you need a quick refresher, here is that equation for the cost based on the priority. DEMR sum I is the priority number, C sub K is the cost. Okay, pumping priority. So what I think is going to happen is we'll have no pumping, apply, and then let's go ahead and save that, and then run MODSIM. Yes. So that ran. I'm going to go right click and graph. We have no flow through this link right here. This is the flow from P1 down to D1. And then we should still have the same flow here. We didn't change anything. Yep. Okay. Now let's change that pumping priority just slightly. I'll click on properties. I'm going to change the pumping priority now to 9899, just a little bit less than it was previously. Apply. Okay. And then let's run MODSIM. Yes. Okay. Let's check out to see if we have any flow now. Here is the plot. And sure enough, we do have flow through that link just as we did before. Of course, now the benefit of delivering water from P1 to D1 is only a benefit of 10 as far as cost goes, which means if this link right here costs more than 10, it's still not going to pump. But if the link cost here is less than 10, then it will continue to pump. So let's do this as one final exercise. Here is the properties for the link now. I'm going to set the link cost to just 11. Click apply. Okay. I'm going to save the model and then MODSIM, run MODSIM. Okay. What I expect to happen is no link flow. So right click, here's the plot, and we have no flow through that link. So no flow from the groundwater. And then let's go ahead and decrease that link cost just slightly from 11 down to 9. Apply. Okay. Now we get a benefit of just 1 for our objective function value, but it should be pumping water and it should be flowing through that link. So let's check it out. Right click and graph. Boom. The pump is running again. It's flowing through that link P1 to D1. All right, well, that's it for this exercise. What we did was talk about groundwater pumping, and we played around with the pumping priority and the pumping cost and saw how that affected the flows in our network.